Okay, we are live on YouTube. So welcome everybody. This is the fourth in a series of 6 classes on science from the LaRouche standpoint. Today we're going to be talking about Gottfried Leibniz, who among thinkers is the one that Lynn then LaRouche most said had an impact on him, in particular as a young man in his early development. So I'm really excited for what we're going to be able to cover today because I think it connects also very well with what we have been doing already. So just to review, the first class we talked about the nature of hypothesis, that knowledge is always temporary, or it's never final. There's always more to know. And that the senses are not the path to knowledge. In the second class, we applied that to a specific science, astronomy, and saw how Kepler abandoned the approach of people before him who just wanted to get the right answer to save appearances. And he said, well, what's making the planets move? And then last week, we saw with Fermat a new kind of cause, final cause, the idea that nature acts in the best way, or in this case, the least action way, the path of least resistance for light. And so what we'll see today is how Leibniz brought all these ideas together in his understanding of a new concept, a new kind of number that straddled the gulf between being and not being, which represented potentiality rather than actuality. And we'll see how he used that. It's called the infinitesimal calculus. I'm going to open with a couple of quotes from Leibniz to give a sense of who this man is. These are not in the reader. So he lived from 1646 to 1716. He's one of those people that the word polymath, was made to apply to. He worked in politics and science and mathematics and philosophy and religion. Here's what he thought about the goal of humanity. Quote, "To contribute to the public good and to the glory of God is the same thing. It seems that the aim of all humankind should be chiefly nothing other than the knowledge and development of the wonders of God, and that it is for this reason that God has given humankind dominion over this globe." So Leibniz was born less than 2 decades after the death of Kepler, and he gave universal scope to Kepler's approach. He made progress towards reconciling the Protestant and Catholic churches. He developed the science of physical economy, and he looked to China as a source of political and scientific leadership for Asia, for Eurasia, and an inspiration to Europe. Here's what Leibniz said about the cultural exchanges with China in his day. So this is from the early 1700s, or late 1600s. "I judge that this mission, the missionary trips to China, is the greatest affair of our time, as much for the glory of God and the propagation of the Christian religion, as for the general good of men and the growth of the arts and sciences, among us as well as among the Chinese. For this is a commerce of light, which could give to us at once their work of thousands of years, and render ours to them, and double, so to speak, our true wealth for one and the other. This is something greater than one imagines." So 300 years ago, Leibniz pushing for Eurasian integration. Here's more what he said. He said, if this exchange of thought continues, I fear that we may soon become inferior to the Chinese in all branches of knowledge. I do not say this because I begrudge them new light. Rather, I rejoice. But it is desirable that they, in turn, teach us those things which are especially in our interest, the greatest use of practical philosophy, and a more perfect manner of living, to say nothing now of their other arts." Leibniz on China. He said, certainly the condition of our affairs, slipping as we are into greater corruption, seems to be such that we need missionaries from the Chinese, who might teach us the use and practice of natural religion, just as we have sent them teachers of revealed theology. I gotta say, that rings pretty well right now. So in terms of when he said that the Chinese practice natural religion, he's contrasting that with Christianity, which is what he says is revealed, that, God directly came, God spoke to Moses, God sent Jesus. So this has been directly revealed to human beings by God, in Leibniz's view. The Chinese didn't have that, but they still arrived at very similar precepts about the nature of the universe. So that's his contrast between natural religion and revealed theology. And this is the last quote of him on China. Leibniz said, "And so I believe that if someone expert not in the beauty of goddesses, but an expert in the excellence of peoples were selected as judge, the golden apple would be awarded to the Chinese, unless we should win by virtue of one great but superhuman thing, namely the divine gift of the Christian religion." Now, so Leibniz is definitely a Christian. He was offered the job of being the Vatican's librarian, a job that he turned down because he was born a Protestant. And it's not that he thought Catholicism was wrong, but he thought the idea of changing represents that these are irreconcilable, and he was hoping to bring the churches together. So he said that wouldn't send a good message if I became a Catholic, because it emphasizes the difference. So Leibniz is clearly a Christian, but you can hear from these quotes of his on China, he's definitely ecumenical. So for more on Leibniz's history as a person, in 2016, which was the 300th anniversary of his passing, I did my part to pay my respects. I did a 6-part class series on Leibniz overall. That's at larouche.info/Leibniz. So in today's discussion, we'll get to know Leibniz by focusing on his thoughts on topics that we've already covered so far in this class series. We'll get to hear his takes on these, and we'll see how he expanded on those thoughts to create his most enduring breakthrough, the infinitesimals, these new magnitudes, potentiality. So let's jump into that. Thinking back to our first class, we encountered Socrates via Plato, and we learned his relationship of the view between the senses and knowledge. In the Wednesday discussion session after the first class, we read some more Plato. We read some more from his Republic, where we see how Socrates demolishes the arguments of tyranny put forward by Thrasymachus. In a discussion about justice, this Thrasymachus says that justice is the will of the stronger. Justice is the will of the stronger. This is the same idea as might makes right, or the cynical view of the golden rule, that he who has the gold makes the rules, as crassly stated by Trump around Easter. Socrates actually showed that the purpose of a leader is to serve the people, not to abuse and loot them. So that brings us to our first reading we'll come back to the Lim quote. I forgot about that. So on page 2 of the handout, we're going to read from Leibniz's Discourse on Metaphysics. I'll pull it up on the screen. A few questions that came in. Do I need to have everyone? In the Leibniz 2 video, you were reading from a set of papers. One thing you're reading quotes. Oh, okay. Yeah, Julian, I can get back to you on that. Julian was asking for the sources of some of the quotes in those Leibniz videos that I was referring to. Okay, so let's do our reading here. And let us begin with, if there's anybody, let's start with an online reader, and then we'll come back to the room. So if anybody...
Yeah, I can do it. Jason?
Yes, go ahead.
Can you hear me?
Yes, please go ahead.
Okay. Beginning Leibniz's Discourse on Metaphysics, 1686, God's Goodness and Wisdom, 1. Concerning the divine perfection and that God does everything in the most desirable way. The most widely accepted and meaningful conception of God is very well expressed in the words, God is an absolutely perfect being, but the implications of these words fail to receive sufficient consideration. To go deeper, we note that there are many different kinds of perfection, all of which God possesses, and each one of them pertains to him in the highest degree. We must also know what perfection is. One thing which can surely be affirmed about it is that those forms or natures which are not susceptible of it to the highest degree are not perfections. For example, the nature of numbers or of figures do not permit of perfection. This is because the number which is the greatest of all, brackets, that is the number of all numbers, and likewise the greatest of all figures imply contradictions, but the greatest knowledge and omnipotence involve no impossibility. Consequently, power and knowledge do admit of perfection, and in so far as they pertain to God, they have no limits. Whence it follows that God, who possesses supreme and infinite wisdom, acts in the most perfect manner in not only a metaphysical but also moral sense. And with respect to ourselves, it can be said that the more we know and understand God's works, the more inclined we will be to find them excellent and conforming entirely to that which we might desire.
Let's take an application of that. When Leibniz is saying that God is perfect, but that there are only some concepts that are susceptible of perfection. So let me ask, what would God say if you, excuse me, what would Leibniz say if you said God is the biggest thing imaginable? He's so big, he couldn't be any bigger.
Well, I'm struggling with, did God really want, everyone to learn about angles and mathematics and goodness knows what else? There is a very natural way of learning with regard to perfection and God. And so I can understand where he's coming from with this piece of writing, but I still struggle, with regard to the math of all of this and why that's important.
Well, let's take a look at the Leibniz quote that we just read and approach that for now.
Can I say something?
So, yeah, go for it.
Yeah, it just seems to me that anything that is discrete, in other words, a number, a thing, or something like that, is not capable of perfection. But what he describes as is capable of perfection is, where am I? Knowledge and omnipotence. Knowledge and power are capable of perfection. So, I mean, the discrete versus the continuous.
So, if God, how would Leibniz respond to somebody who said God is the biggest possible being? God is perfectly huge. Would Leibniz go with that? Would he object to it? What would he say?
He would reject it.
Why would he reject it, Lainey?
Because there would be when you say something is the biggest, you limit it. There's a limitation.
Yeah, he
That's
says
the smartest.
well, he says here in the beginning of the text, God is an absolutely perfect being, but the implication of those words failed to receive sufficient consideration. To go deeper, we note that there are many different kinds of perfection, all of which God possesses, and each one of them pertains to him in the highest degree. So it doesn't sound like he's rejecting it.
So,
well, also big is a spatial conception. It's big implies 3 dimensions, right? And I don't think God exists in that domain.
I'll let everybody a hint. Please look at the second paragraph of this.
The nature of numbers and figures do not permit.
You want me to continue, Jason?
No,
The
I'd like
sound
us
isn't
to-
very good from the room today.
We should.
Can't hear everything.
No, I'd like to address what Leibniz said here. So let's read this through together, the second paragraph one more time. Let me share that again. Okay, so let's look at this second paragraph. Leibniz says, we must also know what perfection is. One thing which can surely be affirmed about it is that those forms or natures which are not susceptible of it to the highest degree are not perfections. So any concept that cannot actually exist in the highest degree is not a perfection, is not part of God. He gives a couple of examples. For example, the nature of numbers. There is no greatest number. Any number you can imagine, you could add one to it and you'd have an even bigger number. So the largest number implies a contradiction. God is not the largest number. He says about figures, the greatest of all figures. Why couldn't you make one bigger? So God is not the biggest. He isn't perfectly huge. But to be perfectly wise, is that he says there's no problem with being, there is an absolute wisdom, and that doesn't make a contradiction. And absolute power, if you can do everything, then there's no limit there. You couldn't be more powerful. So those perfections that actually exist as true infinites are God. But the biggest figure is not.
That's why, particularly in Judaism and Islam, anthropomorphism, or ascribing physical traits to God, is taboo, actually.
Yeah.
It has a lot of implications to that.
Samantha, you got your hand raised. Go ahead.
We can't hear from the room.
Yeah, so if God is all powerful and
Samantha?
all knowing, shouldn't he know the biggest number and be able to make the largest figure?
Samantha, I think you just remuted yourself. Did you want to say something?
No.
Yeah, can you hear me now?
Yes.
Okay, so if God is all powerful, can't he make the largest number or create the largest figure?
Oh, that is a really fantastic question. And this is going to come up. So I promise that we'll be coming back to that. Like, could God, since God's all powerful, 7 is a prime number, but couldn't God make 7 not a prime number? Isn't he all powerful? So yeah, very, very good question. And we'll see how Leibniz treats that. Thank you. Okay, let's go to a reader in the room and we'll continue with part 2 of the discourse on metaphysics.
Sure, we can.
All right.
Go ahead, Harry.
So we were on bullet point 2, those against who hold.
Yeah.
Okay. So we want to start when you get the sound.
Go for it.
Good. Okay. Against those who hold that there is in the works of God no goodness, or that the principles of goodness and beauty are arbitrary. Therefore, I am far removed from the opinion of those who maintain that there are no principles of goodness or perfection in the nature of things, or in the ideas which God has about them, and who say that the works of God are good only for the formal reason that God has made them. If this position were true, God, knowing that he is the author of things, would not have to regard them afterwards and find them good as the Holy Scripture witnesses. And God saw made, and behold, it was very good. Genesis 1:31. Such anthropological expressions are used only to let us know that excellence is recognized by looking at all works themselves, without reference to the entirely external fact about what caused it. This is reinforced by the fact that it is by examining the works that we can discover the workman. They must, therefore, bear in themselves his character. I confess that the contrary opinion seems to me extremely dangerous and closely approaches that of recent innovators who hold that the beauty of the universe and the goodness which we attribute to the works of God are chimeras of human beings who think God in human terms. In saying, therefore, that things are not good according to any standard of goodness, but simply by the will of God, it seems to me that one destroys, without realizing it,
all the love of God and all his glory. But why praise him for what he has done if he would be equally praiseworthy for doing the opposite? Where will his justice and his wisdom? Where will be his justice and his wisdom if he has only a certain despotic power, if arbitrary will takes the place of reason, and if justice is defined tyrannically as by Thrasymachus in the Republic, as that which is pleasing to the most powerful? Besides, it seems that every act of willing supposes some reason for the willing, and this reason, of course, must precede the act. This is why, accordingly, I find so strange those expressions of certain philosophers who say that the external truths of metaphysics, the eternal truths of metaphysics and geometry, and consequently the principles of goodness, of justice, and of perfection are effects only of the will of God. To me, it seems that all these follow from his understanding, which does not depend upon his will any more than does his essence.
I'm gonna switch mics.
Want me to read?
Oh, that's the end of the. Okay. Oh, I see. All right. Good. Okay. So I'm not sure how well that came across, the similarity to Thrasymachus in the Republic, but people notice that difference, that God's, God's all powerful, fine, but Leibniz says people aren't looking at God's wisdom. So somebody in the chat said God could make 7 a non-prime number, but God's not an idiot.
That's not
So is God, does that mean that God is bound? Is he not free if he has to do what's wise? Doesn't I mean, what's the point of being the king if you can't, do a little bit of raping and pillaging every once in a while, right? Well, I mean, God must be so bored if he has to be good all the time. That would be Thrasymachus's view. Yeah, and Leibniz is saying, no, we'll come back to this. We'll think about what this says about freedom. Okay, so for the next part of what we're going to look at is about the
contradict him being all wise and all merciful.
Well, he can do, no, him being able to do anything doesn't necessarily contradict with that, but him actually doing something bad or ugly wouldn't be in keeping with his wisdom.
Yeah.
But he could have.
Maybe we'll get more.
That's his idea. Yep. Okay, so now we're going to take a look at a dispute between Leibniz and Isaac Newton via Samuel Clarke, who is filling in for Newton in this dispute. Let's just put it that way. And this is the next reading. Actually, well, there's Newton, which we're not going to read. So now we're going to take a look at what Leibniz has to say about final cause, and I think that this will resonate with some of what we got from last week. And after we cover this, then we'll get to Leibniz's infinitesimal. So I believe we're due for an online reader, a new online reader, especially if you have never read in this class before. You are particularly invited to raise your hand.
I can read.
Go ahead.
The Leibniz-Clarke correspondence, 1715. Leibniz's third letter. The author grants this important principle, that nothing happens without a sufficient reason why it should be so rather than otherwise. But he grants it only in words and in reality denies it, which shows that he does not fully understand its strength. And therefore, he makes use of an instance which exactly falls in with one of my demonstrations against real absolute space, the idol of which some modern Englishmen, etc. These gentlemen maintain, therefore, that space is a real absolute being, but this involves them in great difficulties, for it appears that such a being must necessarily be eternal and infinite. Hence, some have believed it to be God himself, or one of his attributes, his immensity. But since space consists of parts, it is not a thing that can belong to God.
Okay, let me make a comment here before we continue. So he's referring to, when he says some English gentleman, he means Isaac Newton. Not only Isaac Newton, but certainly Newton. We didn't read this quote, but this is from Newton's Principia, his most famous book. And he says that absolute space, absolute time exist on their own. Absolute time unfolds on its own. Nothing makes it happen. Absolute space is always the same. And that you can actually say whether something is at rest with respect not to your surroundings, but with respect to absolute space. Bodies are in motion or they're at rest, and we have some reference point to actually answer that question from. Although Newton says it's very hard to figure this out because we can't see immovable space. So makes it pretty hard to do that. Okay, so that's what he's objecting to here. So Stuart, one more paragraph, please, number 4, and we'll see how Leibniz responds to this idea that there is this space that exists on its own.
As for my own opinion, I have said more than once that I hold space to be something purely relative, as time is, that I hold it to be an order of coexistences, as time is an order of successions. For space denotes, in terms of possibility, an order of things that exist at the same time, considered as existing together without entering into their particular manners of existing. And when many things are seen together, one consciously perceives this order of things among themselves.
Good. Okay, we'll switch to a reader in the room. Kynan, yeah, go ahead. Jose, could you move the mic right behind you? Careful not to touch the mute button. Okay.
I have many demonstrations to confute the fancy of those who take space to be a substance, or at least an absolute being. But I shall only use, at present, one demonstration, which the author here gives me occasion to insist upon. I say, then, that if space was an absolute being, something would happen for which it would be impossible that there should be a sufficient reason, which is against my axiom. And I prove it thus. Space is something absolutely uniform, and without the things placed in it, one point of space absolutely does not differ in any respect whatsoever from another point of space.
Sorry, if I can, when he says space, he's not just talking about like the distance between planets and stars, but like the air, like between you and me. That's what he means by space too?
Mm-hmm.
Okay, sorry.
Yeah, about where things could be.
Oh, just making sure.
Now from this it follows, supposing space to be something in itself, besides the order of bodies among themselves, that it is impossible there should be a reason why God, preserving the same situations of bodies among themselves, should have placed them in space after one certain particular manner, and not otherwise why everything was not placed the quite contrary way, for instance, by changing east into west. But if space is nothing else but this order or relation, and is nothing at all without bodies but the possibility of placing them, then those two states, the one such as it is now, the other supposed to be the quite contrary way, would not at all differ from one another. Their difference, therefore, is only to be found in our chimerical supposition of the reality of space in itself. But in truth, the one would be exactly the same thing as the other, they being absolutely indiscernible, and consequently there is no room to inquire after a reason for the preference of the one to the other.
So maybe to envision this, would anyone like to put that in their own words? Maybe Kynan, actually.
Say perhaps what he means. Space is really just relationship between the various things that exist. Is that kind of what it means?
And he's bringing up a contradiction here, because he's saying, let's say, okay, so here's the universe, and God makes the universe, and here it is. Well, if God made the whole universe like this, everybody in the universe, no one's going to notice any difference. Like if you're here, this guy's still your neighbor. It doesn't make any, so no one would ever know. So if it doesn't make any difference, why did God choose making the universe here instead of like over here or something? That's the question.
Space is only absolutely uniform, right? That there's no difference between one point of space or another if there aren't like some kind of objects.
Huh? Yeah, that Kynan's asking whether that relies on space being uniform. I'll tell you one thing it definitely relies on is space already existing. Because in this image that came from Newton, God says, okay, time to make the universe. Good thing I've already got this space to make it in, because it was already here. So let me just, where am I going to put it? Hey, I'm God. I'm going to put it over here. That's the Newton view. So why don't you go ahead and start up at number 7. We'll skip 6, which is about time, and it's very similar to space. So go ahead and jump to 7 on the next page, kind of.
It appears from what I have said that my axiom has not been well understood, and that the author denies it, though he seems to grant it. It is true, he says, that there is nothing
Louder.
reason why it is, and why it is rather than otherwise. But he adds that this sufficient reason is the simple or mere will of God. But this is plainly to maintain that God wills something without
Can't hear.
for his will against the axiom or the general rule of whatever.
We cannot hear.
This is falling back into the loose indifference.
Hello.
Amply reputed and shown to be absolutely chimerical, even in creatures and contrary to the wisdom of God, as if he could operate without acting by reason. The author objects against me that if we do not admit.
Yeah.
Okay. All right, keep going. Hopefully it gets better.
Okay. The author objects against me that if we do not admit this simple and pure will, we take away from God the power of choosing and being in a fatality. Sorry, what?
Bring.
Ring, you said being.
Yeah,
Oh, sorry.
what would it mean to bring in a fatality? He doesn't mean to kill God. What does that mean? What words begin in a similar way? Kind of. Can you think of anyone that sounds like?
It means that it is fated and predetermined.
Fate.
Fate.
So fatality here, Leibniz is saying that God wasn't free to choose. It was fate. He had to do that.
Mhm.
That's what he means.
But you're not all powerful if you had to do that.
But quite the contrary is true. I maintain that God has the power of choosing, since I ground that power on the reason of a choice agreeable to his wisdom. And it is not this fatality, which is only the wisest order of providence, but a blind fatality or necessity void of all wisdom and choice, which we ought to avoid.
Hold on. I got a note that they couldn't hear Kynan. Are you also muted when that is unmuted? Because if they're both unmuted, then it just cancels out.
For a while, that's what was happening, but I am now muted. And I regret the problems, everybody, but we're not going to read anything again. I'm sorry. They were on the screen and we have limited time. I'm sorry. Okay. So any other reflections on on what that means before we move on to something else? What's Leibniz's gist here? Why is there no absolute space?
Because if there was just an absolute space, then you're excusing or you're just getting rid of God's reason and will, right? Then you don't take into account that God has a reason for doing things the way he does. Right?
Right.
And nothing, well, I don't know. I was just thinking about the way you phrase it, right? There is already a thing as space. Well, then what? Does that mean that existed before God? Are there things principles that existed before him? So, like, did 7 just exist and then God showed up one day as a prime number? And it's like, sorry, that's the rules. You can't change that.
You know, with the numbers, I'm really not sure what to say. Space, I know Leibniz is saying, he's saying what you're getting at here. That if the space was already there, and God would be forced to make a choice without reason.
Presupposition.
He'd be forced to make an arbitrary choice. I'll put the universe here or here, whatever. But God's all perfectly wise. So why would he do something if it wasn't? I mean, there's nothing wise about putting it here as opposed to here if it's all the same. So, this is just really amazing. This kind of argument leads him to the same view that Einstein has, that absolute space is an impossibility.
God does not play dice with the universe.
Well, that's another thing that Einstein said, and that I think Leibniz agreed with. Okay, so I'm realizing I, as usual, have planned far too much reading for us to be able to get into it. Well, let's see where we go. I really want to get the next one. So could we have an online reader, or we're going to read these very short section from the monadology. Anyone, especially if you have never read online before, you're equally welcome to raise your hand.
Can you hear me though?
Go ahead, Hugo.
Oh, Hugo. Oh, Hugo.
All right. Could you hear me?
Yes.
But the text on the screen, please.
Oh, excuse me. You're right.
Oh, thank you. Leibniz monadology, 1714. Our reasoning is based upon 2 great principles. First, that of contradiction, by means of which we judge false that which involves a contradiction, and true that which is opposed or contradictory to the false. And that of sufficient reason, in virtue of which we hold that there can be no fact real or existing, no statement true, unless there be a sufficient reason why it should be so and not otherwise.
Thank you. You have any thoughts on that, Hugo?
Well, a little tricky. Sufficient reason is like there is one way of doing things, the one good direction of doing things. There you cannot do things arbitrarily. Well, you are free, but at the same time, the things are not arbitrary. So there is some the good way exists. You have to discover. But it's not guaranteed in principle that you. So that's what I think about the underlying concept in sufficient reason, that there is something, there is one way of one good way for reality.
Yeah, thank you. I mean, you know, like you're saying that if it has to be a good way. So part of
Yes.
this thing, he says, if nothing's true, why is it so instead of otherwise? It always means like it had to be a choice. So something's not just true because it's a fact, but for the highest idea is they have to, it's almost like it should represent a choice. Yeah, Rick.
Heisenberg.
Say more about Heisenberg?
Uncertainty.
Yeah. So this definitely doesn't go very well with Heisenberg, Rick's pointing out. So in quantum mechanics, as it's officially understood today, there are some things that happen without a reason. So if you've got some, you know, got some light moving, where go ahead, Rick.
Which Einstein disagreed with. And people like David Bohm came up with theories like hidden variables. So that even if it looks something looks probabilistic, there really is something going on, some kind of confounding physical factor that's leading to it, which would be consistent with this.
Mm-hmm.
Yeah, I mean that's what he's saying in the first part, which is, you know, if your reason, well, yeah, your reason is true as far as it hits no contradiction. But then once you start hitting contradiction, then, you know, it's not that it's happening without reason, it's that it's not happening with your reason, your idea of reason, maybe. Yours being your personal versus.
Well, the contradiction. So in part 31, that there's a more general, maybe I should switch to. So in what he said in 31 about contradiction, that's Leibniz is pointing out that that's a path for knowledge by contradiction. So for just to apply that to what we had about space, Leibniz points out, let's assume space exists on its own. We don't really believe that, but let's just say it exists. Then God has to make this choice, but that is that contradicts his wisdom. God made a choice without a good reason. Therefore, we know that our assumption that space already exists is wrong. So we're knowing something negatively because its opposite is impossible.
Well, that's my attack on Heisenberg, I guess, if I'm understanding it correctly, because by saying it's happening without reason is to give up on your own humanity and this pathway to finding truth.
Well, yeah, I mean, this is the challenge, because then people say, well, you're giving up on your humanity if you're refusing to see what the evidence is showing us. You just have to think something else. So, you know, I mean, Einstein thought, well, we just don't know everything about quantum stuff. There's, as Rick pointed out, Bohm with hidden variables. There's just more there that we don't know. And, you know, I'd like to be open to the possibility that there is something different about the way quantum processes occur in the brain. This is my thought. And that what might seem random in the abiotic domain isn't in a cognitive one. You know, that's like a crack that perhaps something that is undecided physically could be acted upon that way. Rick?
That's interesting.
Yeah, class.
You know, I don't really have a whole class on that. We'll come back to it. So the 6th class on AI is going to get at, you know, what's the difference between a computer and human thinking. And so, yeah, I think that's a spot that it will really come in.
That there's no effect without a cause.
No effect without a cause. That's another. Wait, which one should?
Choose the open mind.
Okay. No effect without a cause. That's another thing that he brings up in some of his other writings more explicitly on that. Okay. So okay, that's good. We got some thinking going, and now.
You're muted.
Oh, hi. I pointed out that Mary Jane had raised her hand, and if she'd wanted to say something, she was welcome to. And while she unmutes, let me read a question that came in from David on the chat. David says, why, if something contradicts a false statement, could it be true?
Should be true.
Yeah, why, if something contradicts a false statement, should it be true? That's a really good point. Just because you contradict something false, maybe there's many ways to contradict something false. So, Rick.
There is a to account for that called many values logics. There are such systems. And if you live in that system, you have a problem with true versus false. Or in mathematics, you have the so-called constructivists who don't accept the law of the excluded middle. Proof by contradiction, they don't accept that. So everything has to be constructed. And that is a body, that is a branch, a way of thinking about mathematics. Thanks.
Okay, so let's go on. We've got, oh, Mary Jane. Yeah, go for it. And then,
Okay, I'm just starting typing. I was just wondering how this squares with Kuza's coincidence of opposites.
well, Kuza's coincidence of opposites is kind of interesting. Kuza addresses this both ways. I mean, he points out also that avoiding contradictions is a path to knowledge, making the same kind of point as here, that it like a proof by impossibility, a proof by contradiction is a way of knowing. And that goes along very well with his sense of, something, what the not other, this kind of approach, his like, opposite of negation way of affirming things. But also, you can apply it that in a higher realm of understanding, sometimes what appears to be a contradiction isn't. And with a higher idea, you remove that contradiction. So that you might take to be the fact that to take the how about the Kepler and the planets? So with the vicarious hypothesis, they came from observations of the planets going this way. Kepler found one parameter for Mars's orbit. Looking instead at observations of how far, up or down Mars was off of the ecliptic, he came up with a different value for the parameter for the shape of the Mars orbit. So, which one of these two is right? Neither of them. From the higher standpoint that Kepler eventually reaches of the ellipse and the speed distance or area time relationship, there's no problem anymore. There is no contradiction because the same understanding accounts for both. So that might be the kind of two ways of looking at about contradictions and opposites. Okay. All right, let's keep going. So I think we're due for I forget, reader here? Yeah, we had Hugo last. Okay, so let's go ahead with the Tentamen Anagogicum. Yes, Jose, go ahead.
Okay. I have shown on several occasions, that the final analysis of the laws of nature lead us to the most sublime principles of order and perfection, which indicate that the universe is the effect of a universal intelligent power. The knowledge of nature gives birth to the arts. It gives us many means of conserving life, and it even provides us with conveniences. But the satisfaction of spirit, which comes from wisdom and virtue, in addition to being the greatest ornament of life, raises us to what is eternal, whereas this life, in contrast, is most brief. As a result, whatever serves to establish maxims which locate happiness in virtue and show that everything follows the principle of perfection is infinitely more useful to man and even to the state than all that serves the arts. Discoveries useful to life, moreover, are very often merely the corollaries of more important insights. It is true here, too, that those who seek the kingdom of God find the rest on their way. The inquiry into final causes in physics is precisely the application of the method which I think ought to be used, and those who have sought to banish it from their philosophy have not adequately considered its usefulness. For I do not wish to them the injury of thinking that they have evil designs in doing this. Others followed them, however, who have abused their position, and who, not content with excluding final causes from physics, but restoring them elsewhere, have tried to destroy them entirely,
and to show that the creator of the universe is most powerful indeed, but without any intelligence. I recognize that it is rather easy to fall into this error, especially when one's thinking stops at what imagination alone can supply, namely at magnitudes and figures and their modifications. But when one pushes forward his inquiry after reasons, it is found that the laws of motion cannot be explained through purely geometric principles or by imagination alone. This is also why some very able philosophers of our day have held that the laws of motion are purely arbitrary. They are right in this if they take arbitrary to mean coming from choice and not from geometric necessity. But it is wrong to extend this concept to mean that laws are entirely indifferent, since it can be shown that they originate in the wisdom of their author or in the principle of greatest perfection, which has led to their choice.
Can you give an example of a final cause? What does he mean when he's using that?
You know, as I was reading, I was thinking, you're gonna put me on the spot. So I should like really try to understand this and read this. You want an example of final cause?
Yeah, because he's talking about final cause. Some philosophers reject final cause, they're banishing it from physics or maybe from thought altogether.
Right.
Do you know what that phrase means, final cause, as opposed to efficient cause? Okay. Rick, yeah, Rick. So Rick was right. I should have definitely had a quote in here that explained what those words meant. So,
Would the principle of least action be an example?
Principle of least action is a good example of final cause. So what makes that a different kind of cause than, like, I don't know, force equals mass times acceleration or something?
Like in that, like, actually has a direction where it's going, that it seeks to reach a point in the least amount of time. And that's like a purpose, like, and expresses an intention. Whereas efficient cause, it's just like something that you observe. But there's like no reason to it. You can't really explain it.
Well, you said force equals to mass times acceleration, like you're observing something as it's going. But with the principle of least action, there's like, as he said, an intention, where it's going, where it'll end up, right?
Yeah.
Right. So I guess efficient cause explains how something is moving, whereas final cause is why something is moving.
Very well.
Look at that.
Yeah. How about that? That's good. Just one other word to it. Kind of said it was a goal for final cause. Jose, you're saying that it's, that efficient cause is how it's moving.
Yeah, like a description.
Yeah, so it's sort of like another thing is that efficient cause is like at a moment.
Yeah, okay.
And final cause is, where are you heading to?
Oh, it's like between like Galileo and Kepler.
Yeah.
Right? Because Galileo can describe to you how something is moving. Or even Ptolemy can describe to you how something is moving too. But Kepler, in order to actually understand how something was really moving, he just had to look at the why. And let's look at the intention of this.
And I'll tell you, he definitely did that when he was looking at, like, why do the planets have the distances from the sun that they do with the platonic solids? That was definitely, like, there's nothing efficient cause about that. I mean, he doesn't think there's a cube, like, pushing on Jupiter or something.
Oh, it's like with Fermat too, like this whole thing about the racquetball or the racket that hits the light down, right? It's descriptive of like what he thinks is happening, as opposed to like the intention of it, of what Fermat thought, which was like, well, maybe there's an intention here.
But what kind of cause would Descartes' tennis racket be?
Well, I guess that what. Friction, I don't know, kinetic, I don't know.
But would it be, would Descartes' tennis racket be more like a final cause or more like an efficient cause?
Inefficient.
An inefficient.
I think efficient cause, right?
Yes, it would be an efficient cause, but it's an inefficient cause.
Yeah.
Right. Yeah. Inefficient. All right. Good. Let's keep going. Jose, you're doing such a great job. Why don't you continue? Oh, hold on. There are some comments here that came in on the chat and look good. See here. We've got if we can't see the reason for things happening or we may not understand why, then don't we look at it from the viewpoint of fate? It was meant to be. Here, let me switch mics for a second. you know, I think this goes to what Leibniz was saying about that even if we don't know what God's intention is or what have you, that there is something, and that yes, and Leibniz believed this was the best of all possible worlds, that it couldn't have been better put together. And sometimes we may not understand why that is, but for example, people say, well, if this is the greatest of all possible worlds, why are people dying of malaria? And you say, well, isn't it in a certain way just for God to give us reminders that we better think and figure things out? You know, a necessity to discover. Just a thought. Okay. Please continue.
Oh, the most beautiful thing about this view seems to me that the principle of perfection is not limited to the general, but descends also to the particulars of things and of phenomena, and that in this respect it closely resembles the method of optimal forms. That is to say, of forms which provide a maximum or minimum, as the case may be, a method which I have introduced into geometry in addition to the ancient method of maximal and minimal quantities. For in these forms or figures, the optimum is found not only in the whole, but also in each part. And it would not even suffice in the whole without this. For example, if in the case of the curve of shortest descent between two given points, we choose any 2 points on this curve at will, the part of the line intercepted between them is also necessarily the line of shortest descent with regard to them. It is in this way that the smallest parts of the universe are ruled in accordance with the order of greatest perfection. Otherwise, the whole would not be so ruled. It is for this reason that I usually say that there are, so to speak, two kingdoms, even in corporeal nature, which interpenetrate without confusing or interfering with each other. The realm of power, according to which everything can be explained mechanically by efficient causes, when we have sufficiently penetrated into its interior, and the realm of wisdom, according to which everything can be explained architectonically, so to speak, whatever that means, or by final causes when we understand its ways sufficiently. Okay, you know, I'm sorry, I can't treat this like our little reading group. This is a class. Go ahead. I had questions, but I don't want to.
Point we're here to talk about.
Okay, I'll go backwards. What does architectonically mean?
Oh yeah, so I think you're right. We should treat this more as a no. I think it means anyone who has an idea of what architectonically means.
Schiller uses it all the time. I forget what it means.
He uses it in the aesthetic layers to, or on the sublime to describe a. To the best of my recollection of Schiller readings, Schiller uses architectonic to describe like a natural form of beauty. Like say, and Lainey, you can add on to this because I know we went through this, but it's been a while. Like for example, an animal like a tiger, just gracefully running in the plains, or horses galloping, or like a butterfly with colorful wings, or even like things like storms. They can be pretty pretty beautiful. Like you look at the space storms on Jupiter, for example.
In thinking about the word, maybe I thought about it a little bit.
Yeah.
Architect, like an architect, puts things together, right, in a way, and everything, every blueprint or structure has a physical reason for why it's there and why it's needed to be there. Why you have columns in the middle of a room sometimes that look stupid, but like there's a reason they're there. So maybe, and he's saying in the realm of wisdom, according to which everything can be explained architectonically, so to speak. So like everything can be explained with reason and cause and just, or like there's a reason why this is the way it is.
The mind of an architect.
Yeah.
Related to an architect.
Okay. Wow.
Bill Ferguson, you have raised your hand. Go ahead, Bill.
Jose basically said what I was going to say.
All right. That's a feat because Bill's really smart. All right. I had another, oh yeah, this whole thing about okay, so as I was reading, I was trying to put this in my mind. For example, if in the case of the curve of shortest descent between two given points, we choose any 2 points on this curve at will,
the part of the line intercepted between them is also necessarily the line of shortest descent with regard to them. It is in this way with the smallest parts of the universe are ruled in accordance. So do you have a way of like, are we gonna do that, or are you gonna explain that?
Let me say that briefly then. Move this a little closer. Just in case. All right, so the curve of shortest descent, we're going to get into that on Wednesday in more detail. But the question is, if you had let's say you had a ball and you wanted it to roll from here to here, what's the path that would get it from here to here the quickest? Would it be a straight line? Roll straight there?
Conventional wisdom tells you so.
Uh-oh, Jose doesn't seem to like that idea. He gave a mixed compliment. Conventional wisdom would say this. All right. So it's actually it's better to have somewhat of a curve, so that at first you start accelerating, build up your speed, and even though the whole thing is longer, you built up some speed in the beginning, and you'll get there the quickest. The question is, there's a lot of different curves. What's exactly the best curve? So leaving it, we're not answering that question right now. Leaving aside how to solve that, what Leibniz is saying right here is, if you have that curve, if you pick 2 points on it, so this is a final cause kind of curve. It's a geometry problem based on a goal, the least time for the ball. If you broke down the problem to say, okay, from this point to this point, what's the quickest curve?
Wow.
It would be the same answer as before. You wouldn't have to draw a different curve. Like instead of we're considering the very first and the very last point, if you just pick these 2 points and said, okay, what's the curve that gets from here to here the quickest? It would just be a continuation. It would be the same as that larger. It would be a part of that larger curve.
Wow.
So, yeah, and the same thing is true for light refraction. The light comes here, boom, and then it bends. So it takes the least time to get from where it began to where it ended up. Similarly, if you said, well, what's the least time path from this point to this point? You're not going to get a different answer.
Right.
You'll still say, oh, it's still, so no matter how small you go, it's always the same.
Okay. I thought, I'm glad you said my initial hypothesis in the 2 points between the thing. I would have thought, great, just another Christochron curve. And then you pick 2 points within that, and then, just infinitely curving. You know what I mean?
Huh.
Do you know what I mean?
Yeah, I do, actually. So now I'm wondering about what I said.
I think that curve would be the same for Christopher curve.
Well,
I think we need a mile-long thing to prove.
Well, let's think more about this one. That's a really good point. Because,
right. Like, why wouldn't?
Because in this case, it already has some speed when it's here. But if we just pick these 2 points, and then it's starting from rest. So you're right. I can see why. Right. Okay.
Yeah, I think that like.
Okay. Well, hey. Good. Thank you. All right. You want to keep reading?
Yeah, sure.
Absolutely.
All right. Okay. Now we find that the ancients already used this hypothesis of the easiest path of a ray which falls on a plane to account for the equality of the angles of incidence and reflection. It is by this same hypothesis that Mr. Fermat provided a reason for the law of refraction according to the signs. But what is more, I have no doubt whatever that this law was first discovered by this method. It is known that Willibrord Snell, one of the greatest geometricians of his time, and well versed in the methods of the ancients, invented it, having even written a work which was not published because of its author's death. But since he had taught it to his disciples, all appearances point to the conclusion that Descartes, who had come to Holland a little later, and who was most interested in this problem, learned it there. For the way in which Descartes has tried to explain the law of refraction by efficient causes, or by the composition of directions in imitation of the reflection of bullets, is extremely forced and not sufficiently intelligible. It shows clearly that it is an afterthought adjusted somehow to the conclusion and was not discovered by the method he gives. So we may well believe that we should not have had this beautiful discovery so soon without the method of final causes. Sorry, he says that the
in imitation of the reflection of bullets is extremely forced. Is that just another?
Well, bullets, tennis balls.
Okay.
Descartes also talks about bullets in some of the times.
Got it. Okay. Right. Just making sure there's.
Did we read this before this part?
Yes.
I think I remember reading this in a previous.
We read a very similar quote from Discourse on, actually, it might have been the exact same quote. It's one of the footnotes from the Fermat book.
Okay.
So, yeah. Okay, so not impressed with Descartes. I'm gonna read a quote from Adam Smith that I think goes at this final versus efficient cause, which I'd referred to this before, but now I got the actual quote. Adam Smith, The Theory of Moral Sentiments. Adam Smith says that the administration of the great system of the universe, the care of the universal happiness of all rational and sensible beings, is the business of God, not of man. To man is allotted a much humbler department, but one more suitable to the weakness of his powers, namely enjoying himself. Back to the real quote. Hunger, thirst, the passion which unites the two sexes, the love of pleasure and the dread of pain, prompt us to apply those means for their own sakes, and without any consideration of their tendency to those beneficent, those good ends which the great director of nature intended to produce by them.
Wow.
What could anyone comment on that from the standpoint of final cause and efficient cause?
I'll only speak if no one else has anything to say.
It's none of your business.
Do what makes you feel good.
Okay.
Well,
Richard Burton, go ahead.
Well, if the cells of our behaved according to such rules, we would all have cancer. It's anarchy.
Uh-huh. Okay, because each cell would just want to do its own growing and not care about the rest?
Yeah, it seems to be that's what Adam Smith is advocating. And it doesn't seem to be a way to produce a successful society.
Okay, good point. So Smith is definitely advocating a efficient. And Smith's definitely advocating an efficient cause approach here. If you do what makes you happy in the moment, something great will happen, but that great part of it, that's none of your business. You shouldn't even think about it. God will do that. So you should live your life according to efficient causes, not by trying to actually achieve anything good, but by enjoying your dinner.
Well, he's just describing some human behavior that's like, well, people get hungry, they have to reproduce, right? And that's like describing this thing, and it's not why do we have these.
Yeah.
Good. Okay. So now let's talk about calculus. So we're going to now get into the infinitesimal, and we'll see what Leibniz has to say about that. So we're going to switch over to take a look at these shapes on the board here. So let's move this for the microphone. Okay, so we've got these hanging chains up here on the board. Would anybody who does not already know for certain what the answer is care to offer a hypothesis of what shape these chains are hanging in? Anyone online? You can type it in the chat.
Like U's.
They look like U's. Okay, yeah, that's true. They're symmetrical. That's one thing.
They look like ellipses.
Okay, so I'm not sure who didn't hear me when I said if you already know the answer, please don't say anything. Yeah. Oh yeah, okay. I'll take this one. All right, thanks. Okay, so a hypothesis that was put forward was these are parabolas. Maybe. Any other hypotheses?
They look like upside down arches.
Upside down arches. Okay.
He's from St. Louis.
St. Louis, right there we go.
Oh, yeah, like-
St. Louis.
The Gateway Arch were built upside down in the ground.
Okay, an
Yeah.
upside down arch, sure.
Yeah.
Is it part of a sine wave?
You lost me.
Is it part of
Sine
it? Is it like a sine wave?
Like a sine wave like this.
Oh,
I know.
this kind of thing. Is it a piece of a sine wave?
Oh,
A sine wave kind of look. So the issue with this shape, someone says ellipse. Could it be an ellipse? Okay. So we've got a few ideas now. How do we how do we know which idea is right? I mean, one thing is we could just measure them and see if they fit. We could try an ellipse, we could try a sine wave, we could try a parabola. That's one thing. But even if it looks right, does that mean that we know we got the right answer? Is that enough? I'm going to put up a picture of. Some would say it's enough if it looks good. I've got a picture I want to share of. Here it is. Second. Yeah. So here, oh, this is of course upside down. I'm sorry, I should have switched everything.
Rotate the screen real quick.
But rotate the screen. So here you can see there's these three curves. One's green, one's red, one's blue. One of them is a sine wave. One of them is a parabola. One of them is the shape of the hanging chain. Now, the blue one, I guess, kind of gives away that it's part of the sine wave because you can, but the green and the red, which one's which? Which one's the real shape of the chain and which one's the parabola? And look at how incredibly close they are.
Well, but
compare that green and the red. I mean,
They look like they intersect at some
they're
point.
almost, I mean, they're very, very, very close.
when you hung that chain up, did you measure the distance between the 2 points that you put them up on, or?
No.
So you just.
Hanging, it does its own thing. So we determine the points that it hangs from and the chain does the rest.
Okay.
So I guess my point in showing this was just that the sine wave, the parabola, and then the actual shape,
they're all pretty
they're all
similar.
very close. So trying to use our eyes to tell them apart is really not, it's going to be pretty difficult.
Well, that's why I was also asking about the distance between the 2 points, because if you could just narrow it a little bit, I guess it changes from one and then to another, right?
Yeah, there's a family of them. So this is a catenary, this is a catenary. This is a catenary just means hang the chain. It's not, it's just, it's a chain. It's the chain shape. It's all catenary. Doesn't mean anything else. Okay, yeah, so there's this whole family of these guys. Maybe one thing you might ask is, does this part right here match this one?
No, what do you mean?
If we took maybe the bottom of this and blew it up, superimposed it, would it look like this?
No, this is narrow. It's,
Yeah, it's narrower. So if we
oh, okay. Now's a good-
Jason,
yes.
if we just used what it looked like to us, wouldn't we be just like Ptolemy and all those guys who didn't want to know why is the way it is?
Yes.
But you're asking why.
Yes, that's right. Well, I'm taking someone's advice here. Okay. I'm sorry, I forgot that you can't do two things at once. Could you say that again, please?
Well, just to go back, we said a couple minutes ago, if we merely looked at the blue, the red, and the green, and it kind of looks like it, then we'd be the same as Ptolemy or the other guys who decided not to bother to find out. It looks good enough, right? So we need to be more like Kepler.
So let's see how we can be more like Kepler. So how would Kepler approach this? So Kepler didn't approach the planets from what do they look like, but what's making it happen. How do we apply the idea of cause to these shapes?
Let's pull out the monochord.
Let's up there. You want to pull it out? Go ahead. Curious to see what you'll do with it. So, any ideas? What do we do with this?
You start measuring something. I don't know. Right?
You're measuring something, Rick?
2 fixed points. You have something with mass being acted on by a gravitational field, which causes the shape to be what it is. So what is this shape in actuality? I mean, isn't that what's causing it, the mass and the action of the gravitational field?
So the question is, how do we, I mean, if there wasn't any, if we were out in the space station, these shapes wouldn't exist. They require, there's this gravitational attraction. But how do we pull it apart? Let me pose it this way. If we were building up this chain, okay, one thing to know it, is that, oops, could I get a helper, please? No, you don't have to hang it back up. We don't need to hang it back up. You're gonna hold it.
Oh, okay.
Okay, so let's do this thing of
And people can't see it in the camera.
Oh, this. Oh,
okay.
Look at it.
All right. So the fact is that, hey, so now this goes like what we were talking about with the brachistochrone. Here, it's actually true. You take off a piece of the catenary.
Yeah.
What remains is still the same catenary. So if you have the problem, you're moving your hand. Try it again. Okay.
Oh, yeah.
Yeah, you're careful not to move your right hand when you do it.
Yeah.
And do it again. Another one.
There you go.
So now we can do it the opposite way. So we're going to start at the bottom, which we can't see. So let's hold up higher. Okay. Okay, so let's start at the bottom. Let's say we want to add one link. We got to get the right angle for that link so that nothing from before changed. We want to add one more link. Well, that's the angle. What angle do we put that link at? So that what came, we're not screwing up what came before. If you put it at the wrong angle, and you let go, the thing shifts. So the way Leibniz approached this was to say what's occurring at each, let's create this shape not as a...
Oh, the pin fell somewhere.
Let's look at this shape not as a final figure, but as if it's in the process of growth. Look at it as a growing living thing. It's growing out of the bottom point. Now, I'm going to save for Wednesday going through exactly how he figured out how you'd add each link, but I'm just going to say it today, and we'll look at it with our eyes, recognizing that this is not the path to truth, but at least we'll know if it's not way off. Okay, so let's do this. This is the bottom. Let's take a look at. We go up 3 links, go up 3 more links, 3 more links, and 3 more links. At each of these spots, we can draw a tangent. Now, if on each of these tangents, we make the base the same length. That's about right. That's about right? The bases are about the same?
Sure.
Okay, so I'll just split each of these as 1. Question is, how high is each triangle? So let's say this is 1. Yeah, let's call that 1 instead. Okay. Let's say this is 1. This height. How tall is this height in comparison?
1.5.
Okay. Well, what we're supposed to see is 2. So I'm going to write 2.
We are way off truth here, and we're
And this one is supposed to be
3.
Yeah.
Oh, three.
Now, I'm just saying, this is what Leibniz said was the process of growth of the thing.
Okay.
So he's saying for each link that you're adding, the angle, not yet, the slope of that link is proportional to how many paper clips do you already have. Or you put it this way, the slope is proportional to your arc length, your length of the catenary from starting from the bottom. That doesn't tell us what the hole shape is, but it tells us what would make the hole shape. So think back to Kepler. Right? Kepler had this idea that the speed is changing based on how close you are to the sun. Okay. But what does that make? That's work to figure that out. Here we've got how each link is added. What does it make overall? That's more work to figure out, which we'll also be doing only on Wednesday. So I want to take a look at what Leibniz has to say about infinitesimals. So we're going to take a look at another reading, but I'm just going to show a picture first. Pose a question. Yeah, this is similar to the picture in your in the reading handout there. The question is that, so you can see what's happening here. There's that slanted blue line. We're just moving the whole line left and right, just sliding it. So now the question is, we take a look at this triangle at the ratio between. Let me see if I can make this just a little bigger for the viewers. Right. The ratio between EA on the top and AC on the bottom, about how much is that ratio?
Looks like 3-to-1, maybe.
Yeah, you know what? When I made this, I made it 2.4 for some reason, which I should have just made it some whole number. But anyway,
Centimeters to inches?
it's 2.4. Yeah, centimeters to inches. Right. This is a centimeter. Here's an inch. So the question Leibniz poses is, he's saying, well, this ratio is going to be the same for all of these triangles. See that they're similar triangles. It's still 1 to 2.4. I picked that number so it would look like the book. Okay. And if we kept going and we went past, we get this triangle, which again, same ratio, 1 to 2.4. Leibniz says, well, what is happening right here? Is there still a triangle? Which side is it on?
Yeah.
Is it a little one on this side or a little guy on this side?
Yeah, it's still like tiny.
So even if there isn't a finite triangle that we can actually see there, there's still, it exists in potentiality. It's ready to come across. Leibniz also has an idea of what he calls the law of continuity. He says that nothing should change by a jump. So laws of motion, the laws of motion for a body at rest should be the same as whatever you would say as if it was moving like impossibly slowly, incredibly slowly.
But Jason,
yes,
isn't that the bottom?
Isn't that the bottom? What do you mean?
I think she means at the line.
Yeah, when there's nothing you can see, then it's the bottom, right? There's no triangle there. At the bottom of the chain.
Oh, yes. At the bottom of the chain. Yeah, perfect point. At the bottom of the chain. Well, I guess actually at the bottom of the chain, you could say, since the slope is proportional to how far you've gone, since you haven't gone anywhere, the slope is 0. But, oh, no, actually, yeah, that's how it applies at the bottom of the chain. So, Leibniz is saying nothing changes by leaps, so there's still like the intention of that same triangle, even at this point. There's something there, it's not nothing. It's smaller than anything you can imagine, but it's not nothing. There's still something there. There's the intent to do something. Let's read a letter that he wrote to Pierre Verignon about the infinitesimal. And then, oh my goodness, I realized I had a whole thing about here on maximum and minimum that we didn't do.
That would have been useful.
Well, we'll come to. Okay, let's come back to that. I want to show another couple examples here. So on the screen here, you can see that we've got this shape. What we're assuming here is you got an outcome on the bottom left, there's a point, and we're adjusting the angle that it's shooting the cannonball at. Right? So if we basically shoot it straight ahead, it's going to hit the ground, and it won't go very far. And if we shoot it almost straight up, yeah, it goes real high, but it doesn't go very far.
Yeah, that's more like a mortar. I'm really bad one at that.
So the question is, how do we find this, how do we get the maximum range out of this cannon here? Now, we saw how Fermat would have solved this problem. Fermat would say, well, you know what? There are pairs of angles that have the same result. So here, this blue angle, it doesn't go very high, so it hits the ground pretty soon. Versus the red one, where it goes plenty high, but it's not moving to the right very much. So they both get to the same place. Fermat would figured out the math to say, well, let me pull these two together. And then when I pull them together, when we pull them together, then we get the best possible path, the maximum. Now, I want to take a look at this is so now this is perhaps how Leibniz would approach this. And okay, this blue curve here, I know it looks very much like a parabola, but it is. You cannot trust your eyes here. Leibniz says, well, yeah, here we go. Leibniz's approach is to say, well, let's do this. At every, so here this chart, going to the right means change the angle of your cannon. The height on the chart, the y-axis, is how far will the ball have gone. Is that okay? Like, okay, let's just put this here. Like at 20 degrees, the ball would have gone 25 meters, the cannonball. Let's just try it out up here. Oops. Okay, 20 degrees. Anyway, and then yeah, look, it's the ball went 25 meters. That's what we're seeing on this chart. So the y-axis is how far it goes. Leibniz says, well, you know what? If you're at 20 degrees, the kind of change here, if you were to increase your angle a little bit, you'd be able to go further. If you're at 40 degrees, if you changed your angle, well, you could go further if you made your angle bigger. If you're at 60 degrees, you overshot it. Now the intent is that you could get the ball to go further if you went to the left. When you're right on top, there's no way to improve. Right? So this slope represents how would the distance the cannonball travels change if I adjusted the angle. Here at this angle, there's no way to go to make it any better. So the way Leibniz would approach the maximum minimum problem that Fermat resolved would be this way. He would say, let's look at where the change disappears. Right?
How did you make that original curve?
Oh, how did I make the blue curve?
Yeah.
Well, you have to do the physics of a projectile. Yeah. Or you ask ChatGPT. That's, I mean, I know how to, I mean, I made the curve, but it was very helpful for actually making the animation. And let's take a look at the catenary. So this is what we had seen on the board together. Is that showing up? Yeah. So the same kind of thing as we move to the right, if we keep the base of that triangle the same, we can look at how, let's say, okay, so we're at the very bottom. The rise for this triangle is nothing. We move along, let's say 0.5 units. Okay. The rise is 0.25. We go twice as far along the catenary. The rise is 0.5. We go the same amount again to the right. The rise is 7.5. What's the pattern here? What's it going to be at 2?
1.5 for every one.
Yeah. So here we are at 2. So this is showing us that that kind of change where the slope is proportional to how far along you've gone. Okay, so we got some visuals in mind. Now let's see what Leibniz has to say about all this. So we'll start with the excerpt. This is on page 6, Leibniz's letter to Pierre Verignon. If we have enough time, let's go ahead and just read the whole excerpt. So I think it was time for someone online, and Susan Wakefield had put her hand up before, and Hugo beat her to the punch. So Susan, you've got dibs now if you'd like to read.
Can you hear me?
Yes.
Okay. Okay, so to make sure that there are lines in nature.
Start at the longer excerpt below.
Yeah. Oh boy. Okay. I believe that in order to avoid subtleties and to make my reasoning clear to everyone, it would suffice here to explain the infinite through the incomparable. That is, to think of quantities incomparably greater or smaller than ours. This would provide as many degrees of incomparability as we may wish, since that which is incomparably much smaller has no value whatever in relation to the calculation of values, which are incomparably greater than it. It is in this sense that a bit of magnetic matter which passes through glass is not comparable to a grain of sand, or this grain of sand to the terrestrial globe, or the globe to the firmament. But at the same time, we must consider that these incomparable magnitudes themselves, as commonly understood, are not all fixed or determined, but can be taken to be as small as we wish in our geometrical reasoning, and so have the effect of the infinitely small in the rigorous sense. If any opponent tries to contradict this proposition, it follows from our calculus that the error will be less than any possible assignable error, since it is in our power to make this incomparably small magnitude small enough for this purpose, inasmuch as we can always take a magnitude as small as we wish. Perhaps this is what you mean, sir, when you speak of the inexhaustible and the rigorous demonstration of the infinitesimal calculus, which we use undoubtedly is to be found here. It has the advantage of giving such a proof visibly and directly and in a way well fitted to reveal the source of the invention, while the ancients, like Archimedes, gave it indirectly in the form of their reductions to the absurd, but they were unable to arrive at complicated truths or solutions in default of such a calculus, though they possess the foundation of the invention. It follows from this that even if someone refuses to admit infinite, and infinitesimal lines in a rigorous metaphysical sense and as real things, he can still use them with confidence as ideal concepts, which shorten his reasoning, similar to what we call imaginary roots in the ordinary algebra. For example, how do you say that?
The square root of -2.
All right, the square root of -2, even though these are called imaginary, they continue to be useful and even necessary in expressing real magnitudes analytically. For example,
let me jump in on that language there.
Yeah.
So Leibniz said something about imaginary and real, and he gave this example of the square root of -2. So if you have a square and if you have a square with a certain area and you would like to ask the question about how long its side is, there is a symbol that gets used that just means the side of the square with a given area. So if you had a square, the area was 4, you can we get this symbol here that means this isn't really where it came from. I think it came from an R root. This symbol means what is the side of a square that has an area of 4. So when you see this square root, root means like side. What's the square side? What's the side of a square? Square root of 4. What's the side of a square of 4? What's the side of a square of 4?
2.
2. What's the square? What's the side of a square of 2?
Side of a square 2.
What's that?
1.4.
1.4. The side of a square of 2. Safe answer. I can't disagree. So we don't have a very good way of saying this, and that's why we write the square root of 2. That's the best way to say it. You can make it, of course, the best thing. Now, how about this? Leibniz wrote the square root, or the side of a square, of -2. How do you make a square whose area is -2? What does that mean? What does that look like?
You say an inverse square. But
would you like to draw that up? I'm wondering what that looks like.
it doesn't look like anything. You'd have to physically take a square and then like grab the and like fold it, pinch it in on itself, and then it doesn't make sense.
Okay. Well, yeah, it doesn't make sense, and that's why the cruel epithet was used for these numbers of calling them imaginary or impossible. So that's when Leibniz uses that word here. Imaginary is the square root of something negative, and you can't have a negative area take its side. So it, as opposed to a real number, that's an example of a real number. It's an actual length that you can draw. You can't draw how long this is. Okay, and so Leibniz here was saying that that the way that these basically won their position as being real, or at least useful, because they were helpful to solve problems. So even before people actually acknowledged that this truly was something that existed, they said at least it's helpful. And Leibniz is saying, well, the infinitesimal, you might not believe in it right now, but maybe it'll still be helpful. So stick with me. I think that's about what he's saying. Okay, Susan, you want to continue?
Okay, I'll start at that -2. So even though these are called imaginary, they continue to be useful and even necessary in expressing real magnitudes analytically. For example, it is impossible to express the analytic value of a straight line necessary to trisect a given angle without the aid of imaginaries.
I'm sorry. I know this is like a specialist thing, but I want to interject on that. So the trisection.
Questo tavolo.
Sì.
Wow. Incredibile, adesso siamo.
So the trisection of the angle, the doubling of the cube, these were impossible problems from antiquity. You couldn't solve with a compass and a straight edge. To cut an angle exactly in thirds, can't do it. Try it, please. Maybe you'll figure it out. So when Leibniz is saying here that we can't do that without the aid of imaginaries, that's a reference to the fact that trisecting an angle is connected with doubling the cube, because generally solving cubic equations used imaginaries. End of perhaps unnecessary footnote. Susan, please go ahead.
So just so it is impossible to establish our calculus of transcendent curves without using differences, which are on the point of vanishing, and at last taking the incomparably small in place of the quantity to which we can assign smaller values to infinity. In the same way, we can also conceive of dimensions beyond 3, and even powers whose exponents are not ordinary numbers, all in order to establish ideas fitting to shorten our reasoning and founded on realities. Yet we must not imagine that this explanation debases the science of the infinite and reduces it to fictions, for there always remains a syncategorematic infinite, as the scholastics say, and it remains true, for example, that 2 equal what's that, 1/1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus blah blah blah, which is an infinite series containing all of the fractions whose numerators are 1 and whose denominators are a geometric progression of powers of 2. Although only ordinary numbers are used, and no infinitely small fraction, or one whose denominator is an infinite number, ever occurs in it.
Okay, let me comment on that. So that series of numbers that he's adding, he claims that it equals 2. You had 1 plus a half plus a fourth plus an 8. Is he right?
No. You would say no.
Who would say no? There's a comment that came in. Richard Burden, go ahead, and then I'll read a comment from Samantha.
Well, if you look at the physical process implied by that series, you can see that it adds up to 2, because you're taking the whole quantity 2 and removing half to get the first number, 1/1, and then removing another half of what's left to get 1/2, and then half of what's left to get 1/4, and half of what's left to get 1/8. And this process goes on forever. And technically, you'll never consume all of what's left. You'll always be taking half, but you never stop doing it.
Well, but it's contained within that, though.
Right.
Well, you sort of have to. So Leibniz is saying again, here's this idea of doing this infinite, which might seem unusual. He's trying to justify the infinitesimal, this thing that's so small that it's not nothing, but it's smaller than anything you can specifically posit. He's saying, well, maybe you don't like that. Let me give you some other examples. So how about infinite? We use that because, like Richard said, you have 1, so that's half of the 2. Then you see, okay, what remains? We've got 1 more here, right? We take half of that. We have our half. So we have 1.5. How much remains to get us to 2? A half. We take half of that. We got a fourth. Now how much remains? 4. So we take half of that. Got it? Okay, well, can you go? So does it ever reach 2? Yes, if you go forever. So do you write forever? No, but as an idea, you can think about it.
But there'll always be something that will remain, wouldn't there?
Yeah.
Well, what about if you go for, what if you had an infinite number of them?
It just gets smaller and smaller.
It does. At any stage along the way, you're right, there is something that remains.
Right. And that which remains, if you have that, you're still not at 2.
If you went forever, let me ask this. After we've added 1 and a half and a fourth and an eighth, how much remains? Right now, how much remains?
An 8.
An 8. If we do this for 100 steps, how much remains?
Whatever that
is.
800.
Pretty small. We should know that. All right. Okay, not necessary to get specific. Okay. Small number. So if you do it forever, how big would the gap be? How much would be missing?
Forever.
Yeah, it would be something like an infinitesimal, wouldn't it? It would be something. It's not. So in a certain sense, it's not nothing, but it's also not any specific something. You know.
Okay.
A new kind of number down there. If I just wants to justify it.
But it's still a really small value. So you're still not at 2.
Well, I would say that you're not any finite distance away from 2. In essence, like it's sort of the concept of 2 comes across in this idea. Like to apply it here, when we drew these triangles, none of these triangles lined up with the catenary. Right, the upper right corner of each of these triangles, it's not where the chain went. Why is that?
Because it's straight lines.
It curves, it keeps changing. If the catenary kept going in a straight line here, sure, it would have gone right along this triangle, but it doesn't. The thing keeps curving. So if we want to build this up properly, how big should these little triangles be that we're building up this catenary?
Really small.
Really, really, really small. And if they're that small, then even if we add a bunch of them, we'll never get anywhere. Unless we have an infinite number of them.
One thing about this example of getting to the 2 is that no matter how long you do this, forever, you'll never exceed 2.
Yeah.
You'll never cross that.
It will never be bigger than
It'll never be
You'll never be bigger than 2. That's right. So we get the infinite. When we apply the infinitesimal here, it has to be this triangle only actually matches the catenary. It has no size.
But you won't reach 2
It's like
without the
square in a
aid
circle.
without the aid of the infinitesimal.
Without this new concept of infinites or infinitesimals are generally incomparable. Leibniz is saying here, you're right. You know,
Well, what's the value of the infinitesimal?
it lets you answer the question of what it happened. Okay, hold on. Let's jump ahead. Let's get the answer to that from Riemann. Okay? And Elliot, I'd like you to read that. So at the on page 9 of the reading.
Page 9.
Yeah, page 9. This is from
Oh, I don't have a page number.
you know, the stupid printer. It's like unbelievable. It didn't know how to print. But it does.
I have page 9.
Okay. I'm sorry. It's up on the screen.
Okay.
Riemann lectures on partial differential equations.
Now, we haven't said anything about who Riemann is. Bernard Riemann, he's going to be one of the subjects of our next class, Gauss and Riemann in the shape of space. And, well, actually, he gave some lectures on partial differential equations. Enough for Gauss. Good intro. I'm glad I interrupted you, Alan.
The subject of these lectures is the treatment of partial differential equations and their application to physical problems. It will therefore be appropriate to begin with some introductory remarks about the relationship between the theory of partial differential equations and physics. As is well known, a scientific physics has only existed since the invention of differential calculus. Only since it became possible to follow the course of natural events continuously have attempts to reconstruct the interconnection of phenomena in abstract concepts met with success. Two things were required for this. First, since simple fundamental concepts with which one could construct, and second, a method for deriving from the simple fundamental laws of this construction, which refer to points in time and space, the laws for finite intervals of time and space, which alone are accessible to observation and can be compared with experience. What has thus been established inductively as fact, that the true foundations of mathematical physics are partial differential equations, can also be derived a priori. True elementary laws can only apply at the infinitesimal level, only at points in space and time. But such laws will, in general, take the form of partial differential equations, and the derivation of the laws for extended bodies and finite time intervals from them requires integrating these equations. Thus, methods are needed that allow for the strict derivation of finite laws from infinitesimal ones, without resorting to approximations. Only then can such laws be tested against experience.
Take a look at this highlight sentence here. Can anybody recast that or restate that in kind of the terms that we've been using today? What kind of cause is Riemann talking about here?
Final cause.
Oh,
So look, on the catenary, he's saying that true elementary laws can only apply at the infinitesimal level, only at points in space and time, only at an instant. It's like with the catenary, the slope thing is only accurate if you don't actually go anywhere. It's only accurate at a moment. So it might result in a final cause, but this is like an efficient cause type of approach. So Leibniz said that there's the kingdom of power and the kingdom of wisdom, and that natural laws, they operate from moment to moment, but why it's those laws, that comes from the kingdom of wisdom. There's the reason for it. And then this last paragraph here, methods are needed to allow for the strict derivation of finite laws from infinitesimal without resorting to approximations. So think about what we had up here with that. We've got something that's true at each point on the catenary, the slope you would add onto it. But how do you turn that thing that you know about each point into a finite, in other words, the actual shape? How do you turn that idea into a shape that you can then see if you're right or not? So how do we turn calculus? How do we? Yeah, I mean, so what we've learned, basically what we have here with the catenary is that the slope is proportional to how far along the curve you are. So this is very short to write. S is the length along the curve, but to figure out what relationship satisfies that's some work, and that's the kind of thing that Riemann's talking about in these lectures. So again, he said, scientific physics has only existed since the invention of the differential calculus. That's Riemann. The ability to think in this way, like this is the beginning of modern physics. Yeah.
So is that you have to go to the infinitesimal to be able to write down an equation? And hopefully that equation is integrable. That's what he means by integrating these equations. So that if you get a solution to the equation, that gives you a description of the physical process. And that's what partial differential equations is all about. Partial differential because it involves several variables. Infinitesimal requires order to set up and solve and solve the using math techniques to solve the equation, to give you insight, if not complete descriptions of what you're getting after, which is understanding physics. Does that make sense?
I think so. Let me read something that came in from the chat too. So this is from Samantha. The curve that we're looking at on the board and starting at the bottom is showing an exponential growth, but the math is showing a constant growth, right? Am I seeing it right? Good question. Let's take a look at this and just restate this again. So this growth, it does, it looks exponential. Zoom, we're going up and up and up and up. Exponential has like a very specific meaning where the way something grows is based on what it already is. And that's not how this one works. This one, the way it grows, the slope for the next added part of it is based on how far along the curve we've gone. That was a very technical answer. Yeah, this looks like it's exponential, but looks can be deceiving. It's not exactly exponential. And then the thing about these being constant growth, the reason that these were changing 1, 2, 3, that the numbers are increasing constantly was because I chose to look at a spot once every 3 paper clips. So if we had looked at somewhere in between, you know, it just kind of depends on how many of these triangles we choose to make. This one right here would be 1 1/3. So you're right that there's a constant growth based on how far you've gone. Wow. We still have not answered the question of what shape this makes. So, except I guess I said it wasn't a parabola or a sine wave. All right, so if there's, given the time, I think time to let me do some wrap up. But if there's any other questions on this, then I'm just talking about where we're heading next. All right.
I have a question.
What is differential calculus? So the differential, so well, what does differential sound like it comes from? What word is the basis? Difference. Yeah. So with Kepler, at every moment, the planet is a different distance from the sun. So the speed is always changing. It's always different. And it tells you at that moment how much your new position will differ from your current one. So it's not focused on what's the result. It's focused on at each spot, how is it changing at each moment? What's the change that's embedded in each moment? With the catenary, okay, as far as we've gone, that tells us the slope. That's telling us how the curve differs if we add a little bit more to it.
That would be very useful for forecasting.
Huh. Well, you know, a big point Lynn makes, he wrote, I meant to pull some quotes from it, but I just didn't, anyway, I didn't make it. He wrote a paper called What Connects the Dots, which is a really good point. You know, if you start with the dots and then you're connecting them, that's one way to think about things. But, you know, reality, something is creating the dots. Something's driving the whole process. So, like, think about it in economy, for example. How much inertia is there in the economy versus how much does the economy have to be recreated constantly every generation or every week or every day or every moment if you're talking about a power plant. You know, there's a principle that's driving the economy. If those principles change, some of them disappear, like investment in infrastructure. If some of them are added, like a new intention, a new drive, a new policy, you know, what you've changed is the way the economy will grow.
Also thinking about like generations of people. I used to think about humanity and life and society as a whole with like this notion that, okay, the old generation is just going to die, collapse all of a sudden, and now this new generation either has to learn what the last did and either keep that going or invent something new. right? Without realizing, oh, actually, we've gotten this far so far from the inception of man to now, right? And so obviously the new generation brings in some kind of new driving force, some new ideas, and it builds upon what came before, thus allowing for a greater increase in growth.
Hopefully. It could add new ideas that cause a decrease in growth, which we've seen recently in some parts of the world.
Yeah.
So, I mean, I'm just saying it's a choice is all. That.
Well, I was just saying, like, is that lawful? That, I mean, are we, if you think about humanity in this great is every generation, whether these ideas are good or bad, is it not lawful that you'll always have something to overcome infinite, always, right?
I think so. I think it would not be the best of all possible worlds if we knew everything.
Right.
There's always I mean, plus for one thing, the number of principles, I'm convinced is uncountably infinite, so we'll never get them all. But yeah, also would be what would we do then? What would be the?
Just look at each other.
Yeah, I mean, you might say, well, we could still, create new artistic compositions. Maybe those aren't limited. Even if we figured everything out about physics, we could still make new symphonies. But I don't think we're going to ever know it all. Because none of our, remember, like what Kuzo was saying, all of our knowledge, it's a surmise. It's tentative, provisional. Maybe that's a good word. Okay. So what we're going to do, let me give a preview for Wednesday then, and for next week. And let me see if there's any other comments that came in.
Just say one thing concerning what Jose said.
So next week, we're going to look at Carl Gauss and Bernard Riemann, how they charted the unseen complex domain of causes and worked out the shape of space, correcting an error that had been in mathematics for 2,000 years since Euclid's day. So we'll figure out such questions as, what is a straight line? What is the shortest distance between 2 points? Things like that. For Wednesday, we will be able to go through the catenary and actually find out why the slope is proportional to how many lengths you've gone. That's one thing that we can do. We can look at Leibniz commenting on Descartes' laws of motion, and we can look at the curve of quickest descent that we had drawn up. How do you get, if a ball is going to roll from one place to another, what curve is the best? And actually answering that question involves Leibniz and Fermat, so it's really very fun to see how Bernoulli solved that problem. And then I think we'll also be able to look at, I don't know if we'll get through all these, but these are on the options, is looking back at Kepler from chapter 57 of his New Astronomy, where Kepler is basically working on doing an integral. He's saying he has a cause, a change, a differential that's always the sine of a certain angle. And it relates to how the planet gets closer or further from the sun. And Kepler says, I think if I add up all of these sines, I get a negative cosine. But I can't prove it. I'm not totally sure. So we can look at geometrically why that's true. And if those terms don't mean anything to you, it's okay. It really will be geometric. We draw it out on Wednesday. Yeah. So, okay. All right. So that we'll end it there. So thanks to everybody for joining, and see you next time.
Thank you.
I'm going to put that.
Thank you.
Oh, the LaRouche excerpt at the beginning. You know what? Why don't we read it now to close? That's a good idea, Elliot.
Excellent.
I'm going to read it because my mic's open. Yes. Okay. So just to end with, this is from LaRouche's Power of Reason, his 1979 version of it, his autobiography, his kind of autobiography. What must a child do to develop his or her mind? He must study the way in which the greatest minds of each age have effected transformations in the quality of human knowledge in the Neoplatonic line of progress, leading through Leibniz. He or she must, at the same time, contrast success with failure, progress with retrogression. By working to replicate the concept-evolving processes of the greatest minds in his or her own mental processes, and comparing that with the replication of the processes of failure and retrogression, the child gauges his or her own mental processes in development with the greatest minds. This approach to education is directly opposite to the inductive method, or the pragmatic method. If one educates a child all the way to the college undergraduate level by piling up successive approximations of knowledge by the inductively or pragmatically ordered approach, the child enters the university with a certain learned accumulation of a knowledge and so-called cognitive skills, but without mind in the proper sense of that term. In point of emphasis, the child has been learning, not developing his or her mind. The only sort of writings which confront the child with the workings of the mind in an immediate way are the philosophical and related works of the Neoplatonic writers. With such writers as a mooring point, the Aristotelian and irrationalist empiricist writers can be studied for clinical contrast. Pragmatist education or value-free educational methods must necessarily destroy the mind's capacity for epistemological rigor. Every important writer has something useful to say. Sort it out when you're old enough. Madam, if you permit that sort of education, you are destroying your child's mental potentialities. In my own experience, I was ready, even hungry, for the indicated sort of educational process by approximately my 12th year. The case of the Brothers of the Common Life and the instruction programs of Hassan ibn al-Sabah are among the sources of encouragement, which suggests my estimate of age range to be approximately correct. There are supporting indications for this in the emotional and related shifts normally succeeding one another in childhood. It is also clear that postponing such discipline to a later age is hazardous. The central paradoxes of physics and other branches of formalized knowledge concur with this estimate for age range. So we might be getting a bit of a late start here, huh?
Yeah.
Should be doing this when we're in middle school. Okay, so thank you everybody, and see you again. Bye-bye.